Okay, welcome everyone. Welcome to our PCS seminar here in Daejeon. And today it's a great pleasure to have with us Professor Auditya Sharma, and he will present us some of his recent work. And I would like to ask our scientific host, Alexei, to introduce our speaker. Please, Alexei.
Yeah, thanks, Dylan. So, so we're having Auditya Sharma today from Department of Physics of Indian Institute of Science, Education and Research in Bhopal. So Auditya graduated from University of California, Santa Cruz, where he was working with young and vector spin classes. After the graduation, he moved to the International Institute of Physics in Brazil, where he had an independent postdoc position for 2 years, which he was working in Tel Aviv University with in the group of Professor Rabani. And since May 2015, he was assistant professor at the Indian Institute of Science, Education and Research in Bhopal. So Auditya has a broad research interests ranging from statistical physics and spin classes to more quantum many-body physics, quantum information, quantum chaos, strongly correlated systems. He's also knowledgeable in the various numerical techniques like Monte Carlo, exact localization, EMRT, and similar. And so today he will be telling us a story about nonergodic behavior of a certain very interesting system. And with this, I conclude. So, Auditya, the screen is all yours. So, welcome.
Thanks very much, Alexei. Thanks very much, Tilan. Thanks everybody from Korea for having me on this program of yours. Very grateful for the opportunity to present some recent work. I'm just trying to see how many people are on board. I count like 6 people. Is that how many people are on, or are there more?
There are 42 participants, including 42 us.
Okay, there we go. Okay, I'm just trying to find where. Okay, I see. I notice. Yeah, okay, that means okay, there's a lot of people on board already, which is very good. Thanks everybody for logging in. So I guess I'm good to start, right? So let me get started without any further ado. So it's this recent work about. Let me make sure that the PDF file is good. Okay, there we go. So I'm going to be talking about interplay of disorder and interactions in a flat band supporting diamond chain. And so this work was done in collaboration with Nilanjan Roy and Ajit Ramachandran, both of whom are also on this Zoom meeting. So if there are any difficult questions, you know, in which direction they're going to get directed. So in fact, I have to acknowledge right away that some of these ideas relating to the diamond chain actually came from Ajit Ramachandran, who used to be a postdoc at your place at the IBS. And so it's a nice, happy, confluence of ideas, which started with Ajit's ideas on the diamond chain. And then we were looking at physics of MBL and also some of these interesting correlation matrix techniques. All of them came together, as I'm going to describe ahead. Okay, so the main message from our work is on this slide. So first of all, we look at what happens when we turn on disorder and interactions on a flat band supporting diamond chain. So the diamond chain already is quite interesting because it has these flat band features. So it's a non-interacting but interesting model. Then we see what happens when we turn on disorder. So even in the absence of interactions, but only disorder, we see an interesting new kind of localization which comes about. So that's also something I will talk about. And so there are these dynamical features which also are part of our study. We show how these compact localized states which exist in the absence of interaction and at zero disorder. So these compact localized states begin to hybridize when you turn on some disorder, and there are these oscillatory phenomena which show up, right? So that's also something we will describe as we go along. Then it's interesting to look at many particle physics on such a lattice, without turning on interactions, right? So non-interacting fermionic statistics also gives us an alternate interesting perspective, and gives us these ideas pertaining to localization. It comes out in justification of these localization phenomena, but from an alternate perspective. And then finally, we'll talk about what happens when interactions are turned on, and how, if both interactions and disorder are sufficiently large, we see a many body localized phase. But there is this intermediate disorder phase where you can get a thermal phase, or which is called an energodic phase. But there is also this small disorder and interacting phase, which we call a mixed phase. So all of this can be nicely represented in this schematic phase diagram. So on the x-axis, we have interactions, and on the y-axis, I have plotted the strength of the disorder. So at the origin of this of this phase diagram is the compact localized point. So then when you're in the absence of disorder and interactions, so this diamond chain has these flat bands and compact localized states. When you turn on disorder and when the interaction is zero, it turns out one of the messages from our work is that this localization is never really destroyed. For any disorder, there is going to be localization, but there are these different kinds of localization which are possible. So if your disorder is sufficiently high, we enter into a kind of localization which is called, which is like Anderson localization, which is a familiar kind of localization. Compact localization is also kind of known in the community, although it's still a work in progress. People are still looking at different kinds of systems where this is possible. But this flat band based localization is perhaps something new and which comes out from our work. And so the idea is that when you turn on a small disorder, all these compact localized states tend to hybridize, and so effectively the localization is not as effective as it is in compact localized case, and in fact it's not even as effective as in Anderson localization. So you end up getting a weak localization in this flat band regime. And so then there is this big region which is called a mixed phase, where some of the eigens, when I turn on interactions and when the disorder is not that high, you have a big mixed phase where you have some eigenstates which have delocalizing tendency, other eigenstates which have localizing tendency. We'll talk about that a little bit later. And then there is some detail. This yellow region is really part of the mixed phase, but a kind of a delocalization tendency within the mixed state. That's also something we'll talk about later. Right. So this is the broad phase diagram, but I will start getting into the details, starting with, first of all, describing what the system is. I believe there are some people who are not familiar with flat bands and so on. So I will spend maybe a few minutes just describing the non-interacting, non-disordered model itself. So the diamond chain is schematically represented in this first figure, right? So one unit cell is highlighted. So you can think of it as containing an upside, a central site, which I'm calling C, and a downside D. And there you can think of it as repeating along the lateral direction. And we imagine that there's periodic boundary conditions, so they turn around and wrap around. So there is going to be translational symmetry in this model, which leads to this macroscopic degeneracy, right? So for the moment, you can ignore actually B, C, and D. I will come back to this in a moment. So the Hamiltonian we have in mind is like here. So there is the hopping part, there is an on-site disorder and an interaction. So if you turn off the on-site disorder and the interaction, that's the flat band diamond chain, which has these compact localized states, which are represented in B, C, and D, which I will again come back to in a moment. So so the thing that is new in our work is both HOS and H interaction. So if you turn on HOS, so we imagine putting these random fields at all these at every site basically, and these random numbers are drawn from a distribution which is uniform and which has some strength delta associated with it, right? So and there is the interaction V operates between neighboring sites. So that's these wiggly lines here, correspond to this interaction. It's somewhat Hubbard-like interaction, but acting on neighboring sites. Okay, so for the purpose of this talk, I have divided, what I want to show into 3 sections. First, I will describe some of the single particle properties. Then we look at these non-interacting spinless fermions, and then finally I'll talk about interacting spinless fermions. So first of all, I want to tell you that there are these flat bands which come about when there is no interaction and no disorder. You have lots of degeneracy which is divided into sort of 3 different lines. You see there is one energy level at -2, another one at 0, and another one at +2 in the units which are given in the problem. And each of these energies correspond to states of this kind. So you see the B, C, and D have they represent the eigenstates involved here, right? So this is sort of one basis in which you can represent some characteristic eigenstates. So if you look at these numbers -1, +1, 0, +1, +1, they are the coefficients associated with these various sites. That represents one compact localized state. It's compact because it's just supported in these 4 sites, and everywhere else it is 0. And likewise, you have another kind of compact localized state which has +1, +1, 2, -1, and +1. And there is a third kind of compact localized state corresponding to a different energy, +1, +1, -2, -1, +1. So you can imagine shifting all of these states by an arbitrary integral multiple of the lattice sites, and therefore you get macroscopic degeneracy. And so you can count, and then it will all add up to the total number of eigenstates in this model, right? So that's what this figure roughly corresponds to. All these energies are macroscopically degenerate, and those compact localized states correspond to them, right? So this is perhaps reasonably well known. Now we have chosen our model. Okay, I forgot to emphasize that there is this minus sign sitting here. So the diamond chain is often studied in a slightly different form, where all these hoppings are taken to be the same, but we choose one of these links to have a negative sign which gets repeated across unit cells. The reason we do that is because we have all the 3 bands involved are flat, right? So if you don't do this, then you can have some of it which is there's a dispersive element also which comes in. And so if you want to turn on interactions and disorder and everything, it becomes rather complicated. So we look at as simple a flat band system as possible, and then turn on these other complications which are of interest for us. So one quantity of interest for us throughout the study, even in the presence of interactions, is this so-called level spacing ratio, which is you just collect all the energy levels involved, right? For a flat band, it doesn't make sense to study this quantity, but the moment you turn on disorder, this is a useful quantity to look at. So you just collect all the energy eigenvalues involved and take the differences in energy levels, neighboring energy levels, take their differences, and then compute this minimum of sk, sk plus 1 and maximum, and then divide one over the other. Each of these numbers is going to lie between 0 and 1, this ratio, and then you take the average of this quantity over all such neighboring pairs of energy levels, right? So if you do this, there is a random matrix theory calculation which tells us that if all these eigenstates are localized, then you expect this level spacing ratio to be around 0.386. So this is a number which comes from random matrix theory. And on the other hand, if all the states are delocalized, then it's going to be 0.528, right? So let me directly go to some results. So we have level spacing ratio plotted as a function of this strength of disorder. So you see that this disorder is starting only around 10 to the minus 3, because this R is not even meaningful to study when delta is exactly 0. You have all this heavy degeneracy then, so you cannot even compute this quantity. But what we observe here is that when the system size is sufficiently large, basically this seems to be consistent with an R value for the localized phase, 0.386 I quote here, and you see that the data for larger system sizes is around that ballpark, 0.86. And also this is also borne out by a study directly of the level spacing distribution. So P of S has this Poissonian dependence with S, and so that's a signature that it's all these eigenstates are basically localized. But the kind of localization is different in as you change delta, as becomes clear when we study the inverse participation ratio. So this is a quantity which pertains to the eigenstates, right? So while the previous one was about the eigenvalues, you can look at how localized your eigenstates are. So you can look at all the eigen functions and study this quantity, which is called the inverse participation ratio, which is 1 in a completely localized eigenstate, but it scales as 1 over n in a perfectly delocalized eigenstate, and somewhere in between it has intermediate behavior. So if I look at the data for this quantity IPR versus delta, so for all these plots that I'm showing, I've turned V to be 0, right? So this is a non-interacting limit. I'm focusing on the y-axis at the moment. So if I look at what happens, yes.
Sorry, we have a question from Dario. Dario,
yes.
please.
Yeah. Hello,
Yeah.
can you hear me?
Yes, I can hear you. Please go ahead.
Can you go 2 slides before?
Yeah.
One more, sorry.
Yes.
I mean, you know, I mean, usually since you have this disorder, you can make an average also over the disorder realization.
That's
and
right.
essentially you can promote R, which here is a global quantity. You can promote it to be RK, in which essentially for each eigenvalue you can do a statistics. So
That's
I was
right.
wondering if you do this, can you see homogeneity with respect to energy, or maybe there are outliers or something like that?
Right. So it is possible to do a sort of energy resolved study as well, right? But
Yeah.
so there is a broad feature that we are looking at the moment. So you see that these error bars, for example, in this figure, they come from the disorder, right? So we look at you know, for a given set of disorder, we'll get one number which comes from averaging over all the levels, and then we use the disorder to get these error bars. But I mean, it should be possible also to look at just, you know, one pair of energy levels and just concentrate on
Exactly.
them.
But do you
also,
expect homogeneity, right?
I think so. So if you look at this, so the error bars are fairly small. So which means that basically this is really just localized as long as the system size is sufficiently large.
Okay, thank you.
Okay, sure. So let me.
We have another question. Ihor, please unmute yourself.
Hello. So just I'm a bit lost. These results are for single particle or for many body?
This is single particle at this point. So I'm looking at yeah, along the y-axis now, right now. So I have turned off the interaction, and I'm just looking at this model where OS and interaction both are absent.
I see.
Sorry, OS is present, but interaction is absent.
Right,
so
right.
Only delta is being increased.
But it's not just that interaction is absent. You are considering a single body problem, not a non-interacting many body problem.
That's right. I will come to non-interacting many. That will be the section 2, right? So
okay,
section 1
thank
is
you.
Single particle problem. Yes.
Thank you.
Sure. Okay, so I'm looking at IPR now. So IPR, single particle IPR, and so this is what the data we have. So you see that IPR is, you know, fairly small when delta is small, and then it tends to become, you know, almost equal to 1 for larger delta. So this is what we are saying is, you know, corresponds to the Anderson localized space. So when IPR is 1, it's a signature of localization, but also the independence of IPR with respect to n is a sign of localization. So the fact that, you know, all these data are basically the same no matter what the system size is indicates that in the entire region the system is localized. But the fact that IPR is relatively low in the smaller delta region indicates that it's a weak localization. So this is what we call as flat band based localization, which comes about because of all these compact localized states that I showed you right at the beginning. You know, when small delta is turned on, they all tend to sort of hybridize, and basically you get a delocalizing effect And so in fact, they can be spread out, but there is a connection to these compact localized states, as becomes further evident when we study this quantity called fidelity. So fidelity is like an overlap between eigenstates sort of at different values of delta. So, and we take these different eigenstates and overlap them, and this quantity is averaged over the entire spectrum. So what we have done here is we overlap the eigenstates at this delta equal to 10 to the minus 3 at the leftmost end, and with respect to various eigenstates at different deltas. So you see that right at delta equal to 10 to the minus 3, this fidelity is just 1. Basically, you're overlapping a state with itself. And then as you increase delta, so what this picture indicates is that these eigenstates are not very far away from the kind of eigenstates you're getting at delta equal to 1. They're very strongly correlated. And then you see that when delta is large, beyond 10 to the 0, that's around maybe around 10, let's say, to be safe, you see that for large system sizes, the overlap is basically 0. So although you're getting strong localization, the nature of these eigenstates is actually very different from the compact localized states. So these are in fact Anderson localized eigenstates.
We have another question from Ihor.
Yes.
Yeah, sorry, I just couldn't catch it. Could you please explain again? So this fidelity overlap, what with what?
Yeah, so I have a bunch of eigenstates corresponding to delta equal to 10 to the minus 3. That's at the leftmost end, right? So I take every such eigenstate and overlap it with respect to some other eigenstate, the same eigenstate, corresponding eigenstate at a different value of delta. So suppose, let's say I'm picking delta equal to 10 to the minus 1. So I have a bunch of eigenstates here, and then I overlap them all with respect to the corresponding eigenstate at delta is equal to 10 to the minus 3, right?
Corresponding meaning in the same position in
Exactly.
sorted energies.
Yeah, so I have a bunch of eigenstates at delta equal to 10 to the minus 3, and then I have a bunch of another set of eigenstates at delta equal to 10 to the minus 1. So I overlap the lowest eigenstate with this, the next eigenstate with this, the third one with this, and so on, and ask how correlated each of these eigenstates are with respect to their counterparts at a different value of delta, right?
I see. So basically, this just shows that when disorder is large, the states don't remain the same, but
yeah, so they're completely different. So they're orthogonal in some sense because you get delta fidelity to be 0 at larger values, right? So although you get heavily, strongly localized eigenstates, they are not really, they have no connection to these compact localized states. That's what this picture essentially shows.
I see. Thank you.
Sure. Okay. So there's another quantity.
Sorry, Professor Sharma, Dario has something more to add.
Yes, Dario. Yes.
Yeah, I mean, very simple. Do you think there are spectral observables that can distinguish the two kinds of localization, or you need to rely on eigenstates? I mean, do you think you can cook up?
So if we look at just the energy structure, they're all the same. It's all going
exactly. But do you think? I mean, this is for level spacing ratio. You don't think that there are other observables built out of the energies that can distinguish, right?
I don't think so. I'm not aware of. Yes.
Okay. Thanks.
Sure.
I have a question.
Yeah.
Can you return to the inverse participation ratio plot?
Yes.
In a flat band, ignore randomness for the moment.
Right.
You have the eigenstates which are degenerate, right? The number of states is equal to the number of sites on your number of unit cells in your chain, but they are all degenerate. So if they are all degenerate, then you can pick any linear combination of them, and they will also be eigenstates.
That's right.
The question is, how do you find the eigenstates for which you calculate the inverse participation ratio? If I were to take only the compact localized states, then the localization length with the IPR will be 1.
That's right. So that's why we don't do this exercise for delta equal to 0. So we have picked a delta which is small but not 0, right? So just like
My question is, in the limit of delta equals 0, what do you get for the IPR?
So if you put delta equal to 0, that's going to be, I mean, because of the degeneracy, then it's you can basically get whatever value you want, depending on how you choose your linear combination of eigenstates.
So are you saying that the finite value, the fact that you get IPR equals 0.2 something is only a result of the randomness, and if you take delta exactly 0, you will jump to 1?
Correct. Yes.
So there must be some crossover there. Can you analytically calculate the changes when you switch on a very small delta? You can do it perturbatively, and I am surprised at this jump. There should be some continuous variation from the value for the compact states to the states which are localized due to the randomness.
Yeah, so I guess there should be some degenerate perturbation theory calculation which should be doable, but we have not done it. Yes, so but it is going to jump, because indeed at delta equal to 0, well, I mean, depending upon which which states you choose at delta equal to 0, it has to have a, it's much more localized than Anderson localized. So it's a strong localization at this point. So, but
so what you're saying is that even an infinitesimal randomness immediately picks linear combinations of the compact states, which are relatively much less localized.
That's right.
I'm very surprised by that.
Well, actually, if you think about it for a moment, it's not that surprising. The reason is, see, you have states of this kind, right? I mean, you have compact localized states of this kind, but if you take linear combinations of such states, which are basically delocalized all over the entire space. So if you take
no, they are not delocalized. They are less localized.
That's right. But if you're taking combinations, they're going to actually spread about the whole space, and that's why there is a delocalizing tendency. The moment you turn on hybridization between various such compact localized states, there is a delocalizing tendency. And in fact, what we are seeing is that the delocalizing tendency is large enough to make these states less localized than Anderson localization, which you get for when the disorder is much higher.
So in your phase diagram, there is actually another phase transitions between delta equals 0 and between an infinitesimal delta.
Yeah,
that's another surprising result of this.
That's right. Yeah, I think more careful studies would definitely worth doing, I think. Yes. Thank you. So should we move on?
Thank you.
Okay, so Fidelity tells us that the nature of the localized state at high delta is very different from the nature of the localized state at smaller delta. And so there is another quantity. I think I'll not go into the details of this. There are two more quantities, von Neumann entropy and Shannon entropy, which also basically tell us that for small delta, they are larger, and at larger delta in the Anderson localized phase, these entropies also show this feature that flatband based localization is a weaker form of localization compared to Anderson localization. So I'm not going to the details here. So we also get complementary results when we look at non-equilibrium dynamics. So we isolate a particle on a site and let it evolve as a function of time and compute how this entanglement entropy spreads as a function of time. So we see that when delta is small, the tendency is to get an entanglement which is larger. So which is again a sense it's causing this wave packet to spread about to a larger width. And when delta is larger, so on the right hand side you see saturating entanglement entropy as a function of delta, but on the left hand side you see the dynamics itself of SA as a function of t. And another interesting feature to observe here is that when delta is very small, delta equal to 0.01, for example, which is the red curve, you get these oscillations, which are characteristic of the effect of these compact localized states. So when delta is small, when delta is 0, you get actually perfect recurrence, which comes from these compact localized states. But when delta is small, you get these oscillations which have a damping associated with them, they decay with time. And this is also seen with revival probability. You can ask, if you start at a certain state and let it evolve, what is the chance that it will come back to itself, as a function of time? How correlated is your initial state with the state at time t? So that's what is defined by this R of t, which is psi in psi t mod of this squared. And so this quantity tends to be very much lower at smaller delta, but much higher at greater delta, which is again a sign that higher delta gives you a more sort of compact representation for the state. So the state is localized, in a stronger way. And once again, we have this oscillatory phenomena at smaller delta, which is characteristic of a role of these compact localized states. And the dynamics of the width of the wave packet also bears out a similar feature, and the width being relatively larger at smaller delta and reducing at larger delta. So Anderson localization is stronger localization. And so this figure shows you how the tendency of your wave packet to spread. So this is the on-site occupation probability. And so you see that when delta equal to 0, when you have this fully compact localized Hamiltonian, you let it evolve and you ask the spread of your wave packet, it is just localized in a very, very tiny region. And then when you see that the green data is when the delta is very large, once again you get a rather nicely compactly localized region in which your wave packet is contained. But it's not as strong a localization as compact localization. But on the other hand, for small delta, you see when delta equal to 0.001 j, delta, that is the red curve, you still get localized spread, but it is a weaker localization compared to Anderson localization and compact localization. So from the single particle picture, we managed to get this feature that you have compact localization at delta equal to 0. And
can I ask another question?
Yes, yes.
All of these results are for the bands at energy +2 or -2. Am I right? Because you had that bond equal to -1.
That's right.
Have you done the same analysis for the flat band at energy 0?
But I
that
think
is different because, for example, the compact localized states are on 1 unit cell, not on 2 unit cells in that case. Here, so you did only the compact states for the 0 energy band are not like this.
But are like here, no? So I'm trying to recall which. So there are these 3 different kinds. So there's B, C, and D. So they're all localized on actually 2 unit cells, right?
Here, but not in the case of energy 0. At energy 0, the compact states are only at U and D. U equals +1 and D equals -1.
But is that for this band with one of the bonds being -1, or all of them are
no,
1?
No, all the bonds. If the band at 0, you have to take all the bonds equal to each other.
No, we have not looked at the model with all bonds being the same. We have only studied the model with one of these bonds being -1. Yes.
Okay, and then you say these compact states also apply to energy 0.
Right. Yeah, I mean, yeah. So it is worth also considering the other model where all the bonds are just +1, but then you also get these other dispersive bands. Probably then you have to be careful to isolate the behavior of just the compact localized.
Yes, but you're telling us about the flat band. So the question is how universal your results are.
Right, that is something
even qualitatively.
Right. We have not looked at the other one, the other model. That is something.
Thank you.
If I maybe can add to that, actually, Amnon, this has been studied way back in 2014. So if you have one flat band and maybe other dispersive bands, but that flat band which you look at is, say, gapped away from the rest of the spectrum, and you add disorder similar to the one which Auditya now discusses, so say on-site disorder, then in the limit of weak disorder, you will get a finite localization length and the finite participation number, which is different from your compact localized state picture. So you will get pretty much
the same as he gets.
You get pretty much a similar result,
Okay.
a surprising one, as the one we have seen here, for one flat band which is kept away from the rest of the dispersive spectrum.
And that's universal for any kind of disorder, or?
Well, that is maybe a deeper question. Let me not answer that one right now.
Yeah.
Sorry.
Okay, so let's move on to the second section, which is about non-interacting spinless fermions on the same lattice. And so we see that the results sort of justify the kind of features that we have already seen with just single particle physics with no interaction. So we look at non-equilibrium transport properties. So starting from an initial many body state of this form, where we fill this lattice with a filling fraction of 1/6. And so basically we look at every alternate unit cell is occupied by a particle. So there's a fermion sitting only on the C sides of alternating unit cells, and then we let it evolve as a function of time. And study growth dynamics of entanglement entropy, which in this case can be computed very effectively with the help of correlation matrix techniques. So there is this method popularized by Peschel and co-workers, so who show that in fact if you just look at the correlation matrix and study this L by L matrix, you can work out the entanglement entropy in terms of this formula. You just find all the eigenvalues of the correlation matrix and compute this object, trace over C log C plus 1 minus C log 1 minus C with an overall minus sign, and you get the entanglement entropy. You don't have to diagonalize the full reduced density matrix, which will be a much bulkier object, 2 to the L by 2 to the L, and this allows us to in fact study much bigger system sizes, even when you have many particles which are non-interacting. And so here are the results. If you look at subsystem size dependence with respect to L, so we see that basically this entanglement entropy simply does not vary as a function of L, which is a characteristic signature of localization, right? So the states are located in some small region. Therefore, as you change L, basically entanglement entropy is not sensitive to it. But we notice that the value of this entanglement entropy itself is much smaller when delta is much larger, and it is larger at smaller values of delta. Once again, a feature which corresponds to this weak localization at smaller values of delta and strong Anderson localization at larger values of delta.
Sorry, Aditya, I think I lost you or you lost me.
Yeah.
So again, so you have a non-interacting many-body system.
That's right.
How many particles do you put in there? Is there a filling factor? Which
yes. So the filling fraction is 1/6. So
okay.
What we do is we look at every alternate unit cell has a fermion sitting on it in the central site, and so it amounts to a filling fraction of 1/6, and then we let it evolve as a function of time. It's
every second unit cell.
Yeah, every second unit cell has a particle sitting on only the central site.
Okay. Why that, or what happens if you choose a different
we could
site?
choose we could. I mean, it's just we just chose one such state, and it's I mean, it extends to the interacting problem as well. So we just chose something where when you turn on interactions, you don't have you cannot go to very large system sizes. So then 1/6 turns out to be a good choice.
If I remember correctly, the zero energy flatband of the single particle problem will then not be addressed, right, by these states, because or no, I'm saying something wrong, because you add disorder anyway. So everything,
So everything is going to get mixed up. Yeah.
Okay.
So in this state, even if you switch on the interaction, nothing happens to it, right? Because there are no nearest neighbors.
Well, I mean, something will happen.
But am I right that if you just take that state and calculate and apply the interaction operator on it,
On
You
that
get
state,
zero.
on that state, yes, yeah. So there, yeah, exactly. So the interactions don't count as far as just that one state is concerned. But if you allow it to evolve as a function of time, then of course all the eigenstates will play a role. Then it does matter what the interaction is.
Any motion will cost energy for the interaction.
That's right. That's right. Right. We'll come to that in the next section. But I mean, the reason why we choose 1/6 is because it's convenient to work with 18 sites. And then it's just convenient. It's a convenient filling fraction when we have interactions turned on, and we have this constraint about how large a system size we can study. Okay, so the yeah.
Sorry, we have another question by Dario.
Yes, go ahead.
Sorry. It's really a stupid question, but just because I'm ignorant. What's the point? I mean, in a system without interaction,
right?
What's the point to study the multi-particle thing? I mean, I thought that everything is just single particle and
yeah. So the idea is that so you will see in a moment that this non-interacting many particle is somewhat in between the single particle and interacting many particle. There are some features which are a little different, right? I mean,
you still have the Pauli principle. That's why
right.
you have effective interactions.
I see.
Right.
Okay.
Yes. Pauli principle is in play.
Okay.
Yes.
Okay, got it.
Sure. So you will see in the next slide, in fact, that there is something which is a little different from just a single particle case. So if you look at the growth of entanglement entropy, so you see that as a function of time, indeed you get for small delta, you get these oscillations which are damped, which is characteristic of this role these compact localized states tend to play. And I mean, if you look at the saturating values as a function of delta, you see that although at high delta it's small and low delta it is relatively large, there is this in between delta, there is this so some intermediate delta where there is a tendency for SA infinity to actually go up. So this is this is a feature which comes about because of the Pauli principle in play. So there is interaction it does play some kind of a role. And I mean, exactly why it happens, I'm not entirely sure, but this is a feature that you will see again when interactions are turned on as well, right? So in that sense, there is this sort of bridge between single particle characteristics and many particle characteristics with full interactions on. So there's another quantity, yes. So there is another quantity which is worth investigating, and that's called this imbalance parameter. So what we do is we look at the occupation at NIC. So this is tuned in such a way that it corresponds exactly to the initial state which we consider. So you see in the numerator we have the occupation on the central side minus NIU minus NID, and in the denominator you have it's just a sum of all the particles. So in this case they all add up to capital N over 6. So the filling that we have chosen is 1 over, filling fraction is 1 over 6. And in the numerator, it's tuned in such a way that at time t equal to 0, this imbalance parameter is exactly 1. So it picks out only those points where there is a particle, and then you subtract out 0 according to positions where there isn't a particle. So you can, just staring at this equation for some time, you can convince yourself that if you're in a fully delocalized state, many body state, then this imbalance parameter should go to -2/3, whereas if it's a perfectly localized many body state, you'll get IB equal to 1, right? So, I mean, it just comes about from putting these values for NICs and NIUs. This quantity has been just designed so that you get these two different numbers for these two different kinds of states. So if you look at the results, you see that this imbalance parameter is quite large. It's not exactly 1, but it is large and close to 1 when delta is very large, right? So that's in the Anderson localized regime. Indeed, IB tends to go to a much larger value, but when delta is 3 or delta is 50, delta is 0.01, you get a lower value. It's not -2/3, but it's a negative number, indicating once again this kind of relatively more delocalized nature, but still these states are localized. But and on the right hand side, you see that this lack of dependence on system size once again is a signature that it's really, these states are all localized, but the value of IB is in fact much smaller, right? So this quantity will come back again when we study interacting fermions. And so we are ready to start the next section, right? If there is any pressing questions, we can take
question.
Yes.
Why couldn't you put all the particles on every second B site, not up site?
We could
So
do that.
instead of
yes.
putting them on the central every second site, you could put them on the upper every second site, and then your IB will be -1, I think.
Then we could design it in a different way. IB can be defined in terms of the
but that's a possible state of the system which has the same energy.
Right. Yeah, we could definitely do that as well. I don't know if that's going to give us any significantly different results. Yeah, so I mean, we just chose one.
I'm just wondering why your numerics doesn't pick that as a possible state as well.
No, I mean, I'm not sure what you're saying. So, so given the initial state that we have chosen,
U to be 1 for every second site.
Okay.
Then this will result with -1, right?
But will we study the same imbalance parameter as here, or will we study a different quantity? If we start with a different initial state, we might pick a different IB of T, no? The definition itself.
So the result depends on the initial state.
Right.
Which means you have not explored all the possible states in the system for this Hamiltonian.
No. So this IB of T has been sort of carefully designed to put IB equal to 1 at time t equal to 0. We start in a localized state, and then we ask what is the tendency of the Hamiltonian to do to such a state. You are in an initially localized state, but does it keep it localized, or does it tend to take it away from localization? Okay, so let's look at interacting spinless fermions. So when we turn on interaction, so first we study this level spacing ratio, and as a function of delta again, but now we also have various interactions we can consider. So I have these 3 different, so now of course we have this severe constraint which comes about because we can only study system size of up to n equal to 18, and these different fillings we can get data from, but we no longer have these nice correlation matrix kind of techniques are available. It's just brute force diagonalization. We have to work out everything purely numerically. So the level spacing ratio here is plotted as a function of delta for in A, B, and C for 3 different fillings: 1/9, 1/6, and 2/9. And for all these plots, I'm fixing the system size to be n equal to 18. And so what we notice is when V is large, so let's look at the green data. So when V is large and when disorder is, there is a point in disorder where there's a peak in R, and that peak value corresponds to the ergodic phase, right? So the value goes to 0.529 as you increase the filling fraction, right? So if you look at A, B, and C, the value of the peak, the green curve, is only around 0.4546 in the first one, and it tends to go towards 0.5, and then it goes further up, and presumably it will go to around 0.529 when the filling fraction is relatively high. So this is
excuse me, we have 2 questions. Ihor was first.
Go ahead.
So I wonder here, when you calculate R, do you calculate it directly or with some treatment or tricks? Because it seems if interaction is very weak and disorder is very small, the many-body levels should form, so to say, multiple bands. So just the initial 3 flat bands are combined in many ways. In the spectrum, there should be a lot of huge gaps and nearly flat, a lot of nearly flat groups, which should be very problematic to calculate R.
That's right. That's why we start delta from 10 to the minus 3. And yeah, I mean, small interaction is not enough to break the degeneracy. In fact, large interaction is also not enough to break the degeneracy. We have to turn on disorder. Disorder definitely breaks the degeneracy. And so you see the data is all presented from 10 to the minus 3. But maybe there is a way to do some analytical work in the limit of small delta, but not not zero, but slight small delta.
But that's not what I mean. That's the problem is not the break in degeneracy. The problem is that in the spectrum there are a lot of almost degenerate groups of eigenstates, which is okay. They still may have a Poissonian or Wigner-Dyson distribution in this tiny window. But between those tiny windows, there are a lot of gaps. Maybe here it's not a problem because I think basically you have only 3 particles. But it seems to me that the definition of R in that limit of Wick disorder and V should become ill-defined for a sufficient number of particles.
But so that comes about because of the degeneracy, isn't that right? You have many energy levels sitting basically at the same value. So it's not very clear what you mean by differences in energy levels and dividing by another difference in energy. Is that what you're saying?
Well, I'm saying that there are a lot of gaps around those, so to say, flat bands already, which are already much more than 3 because of many body effects. So there are a lot of these tiny islands of energies that all have small gaps between themselves, which is by itself is okay. But then there are a lot of such islands that are additionally separated by already not something of order of delta, but separated by something of order of 1 of the initial gaps between the flat bands.
I see. Okay, I see. So you're saying that we should actually be doing sort of an energy resolve. We should consider only one band and do it separately for each of the 3 bands.
I don't know, but for 3 particles,
probably there will be many
than...
outliers.
Yes.
Okay.
So I think if you plot distribution of gaps, you may see a huge.
But these outliers are not really going to affect it in a bad way, in the sense that you see it's only like there are these 3. So you have this large average that you're taking. No? So when you define R, so you have an average over n values. If there are only 3 of these which are outliers, I don't know if it's going to.
That's the case in a single particle problem. But if you have 100 non-interacting particles living in 3 bands, you're getting an exponential number of bands because
just three, because you take the difference between, let's say, the one with the highest energy of the lower band and the one with the lowest energy in the higher band, but it's just 1 in that case. So remain 3. You don't take all the differences.
Well, you do. For the full spectrum, you do.
No, because you take the differences only between the adjacent levels.
Right.
If you have 100 particles that can live in energies -1, 0, 1, you have energy -100, -99, -98, and up to 100. You have 200 many-body energy states.
But the huge difference will be between islands, and for each of couple of islands, you take just 1 difference and not many. Okay, maybe it's better to discuss later.
Yes.
Yeah, I think I agree with Dario, right? I mean, so the point is that even though you have this sort of big structure which comes about inside each separate island, when you jump from one island to the next, it's just one big jump. And then there's another big jump. That's all. That's not going to be a macroscopic number, right?
Well, yeah, maybe it is macroscopic, but maybe it's much smaller than all the others. Yeah, I think that's true.
Plus, here you are at fixed filling fractions. So you have either 2 particles, 3 or 4, right? Left, middle, and right
that's
picture
right. Yes.
On 18 sides.
Yes.
So it's still kind of few particles.
That's right. Yes. Okay, so yeah, so this is what we have. So if you look at these features, if at smaller v, so if I look at the black curve, so I am able to discern a bump at a smaller value of delta, and so this corresponds to this what we highlight as a delocalization tendency. Although broadly in this region you have a mixed phase in the sense that this r is neither 0.529 nor is it 0.386, but it's somewhere in between, which comes about because of mixed character of these eigenstates. And there is this blue region, which is the ergodic phase, which corresponds to the peaks. So if you look at around delta equal to 1 or delta equal to 2, that's where you have this peak, right? So this is the broad feature to take home. And then I'm reminding you of,
yeah, in particular, I believe that maybe in that region could be interesting to do an energy resolved study.
Right.
And also another comment, did you try to understand if let's say the critical disorder at which you have that peak is drifting with the system size or not? I know that is hard because you cannot go to very large sizes.
Yeah, I will show you system size data in a moment.
Ah, thanks. Okay.
Yeah. So if I look at so there you go. So there is this system size data. So the level spacing ratio is a function of disorder strength delta. For I'm keeping V fixed and also filling fraction fixed, but I'm changing n to 12, 18, and 24. This is what we are able to do. And so we see indeed that there is it's a genuine peak at that point. So there is a tendency for it to go to the ergodic phase at that point, as you will also see from non-equilibrium dynamics also shows out this feature, which I will also show you in a moment. So there is this quantity called MIPR, so which is the many body IPR, which also we compute. So which is basically you expand it in this Fox space. You have all these coefficients, and then you use all these coefficients to compute this many body IPR. And so if you're in an extremely localized state, only one of these coefficients will be active, and then you would get an MIPR of 1, which is what is seen for a many body localized state. And on the other hand, if you have perfect delocalization, then you expect all of these C's to contribute, and then you get a 1 over D kind of value. So we study MIPR as a function of delta and for all different V's. And once again, this data is for these 3 different fillings, 1 over 9, 1 over 6, and 2 over 9. And so we see that for large delta, there is this tendency for MIPR to go to 1. So that's this many body localized. So the green region you get when you have large delta, and and some interaction, and large delta tends to take your MIPR to become very large, and it's really in the many body localized phase. But if your delta is relatively small, that's the mixed phase. And then there is this in between region where you get this ergodicity, which manifests itself as a dip in this MIPR data. And we also look at scaling of MIPR as a function of 1 over D. So you see that this green curve corresponds to very large delta, which is the many body localized phase. MIPR basically doesn't vary much. So these coefficients gamma are the power to which 1 over D has to be taken to fit this data, MIPR versus 1 over D. And we see that the blue data is as close to just a linear behavior as possible. So you get a gamma of 0.9, and so this blue data is for this in between point. So you have this ergodic point sitting at these special values of delta, and so there you get a almost linear type of behavior of MIPR versus 1 over D. But as you go to higher values of delta or lower values of delta, you tend to see more sort of localized. For lower values of delta, you get, of course, sort of in between behavior. That's the mixed phase. But when delta is very large, you get the many body localized phase. So is there a question somebody wanted to ask? I thought somebody said something. Okay, that's fine. So in figure B on the right hand side, you see MIPR data versus 1 over D, but for different interaction strengths. So where I have kept delta to be fixed at 0.01. So we are in the the mixed phase here. So you see that all these curves have exponents gammas which are quite far away from 1 and also from 0. So which is basically a signature that the states are unable to make up their mind as to whether they want to be localized or delocalized. So MIPR scaling for fixed filling is also worth considering. So this is again a log-log plot with MIPR versus 1/d and different values of V. So we see that when V is very large, you get relatively smaller gamma, and delta again is fixed in the mixed phase, right? So this figure sort of shows data similar to what we saw in the previous figure in part B, except that now we have the filling is fixed and its n is changing, so system size is changing, right? So it's complementary data. So now we come to this energy resolved data, right? So this is something we also did study, but maybe it's worth looking at it more closely. So you see that we can study MIPR for all the eigenstates. So we have put all these eigenstates inside this window from 0 to 1. So this epsilon index measures relatively where you are among the various eigenstates, and you see that there are certain eigenstates where there is a tendency for this MIPR to shoot up and then it comes down, and there is this sort of tendency for it to go back up and forth and up and down, and which is even more evident for small v's. So if you look at the red curve, you see that it dips and then goes up and comes back up. So there is this delocalizing tendency, we call it, in the phase diagram, right? So which is also seen for certain along this 45-degree angle. When V is roughly the same as delta, it is around that region that we tend to see this delocalizing tendency, which comes about from various eigenstates, right? So this data is sort of energy resolved data, and which is also similar results are seen when we look at entanglement entropy. So you see entanglement entropy for half chain entanglement entropy, which we have computed for every different eigenstate, and you see that when V is very small, 10 to the minus 4, and then we look at 10 to the minus 2, right? So if the blue data shows you this sort of delocalizing tendency, and then it comes back to again localized behavior, and then again a delocalized tendency on the left side of figure, and on the right hand side we see that SA of infinity tends to be this sort of broad high value when for the blue point. Blue point is that the ergodic point when delta equal to 2 is this very special ergodic point, or in some small region of delta there is this ergodic behavior. You see that all these states tend to have a sort of delocalized character, and when delta is very large, again you get this many body localized phase. Clearly there is very localized behavior is evident from the very small values of SA of epsilon for all eigenstates. Whereas when you have when you're in this mixed phase, there is this tendency to go back and forth, some delocalizing character back to localizing character, and so on.
Excuse me, we have another question from Ihor.
Yes, please go ahead.
So on this previous energy resolved pictures, so for example, V 10 to minus 4 and the delta 10 to minus 2, we discussed a lot of bands. So those dips, do they correspond to the edges of those bands?
Yeah, so that is actually worth exploring more in the context of this discussion, maybe. But actually, we did not look closely enough to see whether they correspond to these broad jumps from islands that we were talking about. I don't know, maybe. Yeah, but there is this kind of a structure. There is this sort of island-like structure is indeed evident here. And that is showing up for small interactions. So perhaps maybe that's what it is. Yeah, but it's worth looking at it more closely.
See, thank you.
Yeah. Okay, so we also looked at non-equilibrium dynamics. So here we fix the filling fraction to be nu equal to 1/6. Again, start with an initial state, just like we did with non-interacting fermions. So n equal to 18 is what we can go to here. So every alternate central site of your diamond chain is occupied by a fermion, and then we let it evolve as a function of time. So we see once again this damped oscillatory behavior for small delta is present even when there is interaction, right? So this is like I guess there is a recent work by Alexei and co-workers, I think, who look at the the interacting model when delta equal to 0. Perhaps so there is some kind of is there a comment? Somebody? Oh, question. Should yeah, you want to ask a question?
No, I think some people didn't mute their mics.
Oh, okay. That's fine.
That would help probably, but it's just some random noise coming in.
Okay. I see. Okay. All right. So yeah, I think there is this recent work of Alexei, and I don't remember the details, but they did check what happens when you take a model of this kind, the diamond chain, and turn on interactions, but there is no delta. And so then I think there is this tendency. So like you see here in this, the red curve here is showing you damped oscillatory behavior. So I actually would like to explore this further and see what happens when you just turn on only V, but not delta. It does not break all the degeneracies. There are some of these degeneracies still present, and maybe there are some special resonances still available, which causes these kinds of oscillatory behavior. Recurrence is still seen. And so the broad picture to take home from here is part B, right? So part B of this figure is it shows you how the saturating value as a function of delta has this peak at this special value of delta, and that corresponds to the ergodic behavior. But when V is small, the peak appears at a much lower delta, and that's this delocalizing tendency that we call, and that roughly happens around V equal to delta. So that's why it lies on this Y equal to X type of axis. Okay, so return probability dynamics once again shows you these sort of recurrent damp dynamics when delta is small. Here again, I've put V is fixed to be 1 on the figure on the left hand side, but you have different interaction strengths on the right hand side, and R infinity as a function of delta once again gives us the same picture. So there is this dip right at around delta equal to 2 or so when you have the ergodic phase, and at small delta you have intermediate behavior, and large delta you have a many body localized phase. Yeah, imbalance parameter, once again it's the same imbalance parameter, is the same kind of initial state. So it starts with a localized state, so IB is equal to 1 at time t equal to 0, and then as you increase time, you see that if you're in the many body localized phase, you don't go very far away from 1, so it just tends to sort of stick around the same kind of initial state. But if you're the blue curve, for example, shows you that it gets pretty close to this -2/3 value, right? Meaning that all the sites basically get the same kind of occupancy. If you put all Ni to be 1, that's the delocalized state, and then you compute that quantity IB, you will get -2/3. So here you notice that it does not quite go to -2/3, but it goes to around -1/2. So it gets pretty close to the delocalized state. But for small delta, this is this in-between behavior, right? So that's the mixed phase. Okay, so yeah, once again, all of these data are consistent with this broad big picture that which hopefully I've tried to convince you about, which is that this model is interesting even when we turn on interactions. When we turn on disorder, just the disorder itself gives us these different kinds of localization. Compact localization is the strongest kind of localization we see among all of these different localization. There is this new kind of localization which we have called flatband based localization, which is a weak kind of localization which comes about only for small disorder. to be compared with Anderson localization, which kicks in for larger values of disorder. We are also able to find complementary results using wave packet dynamics, non-equilibrium dynamics, studying a bunch of quantities. They all consistently suggest this picture, both in the both with just single particle picture and also with non-equilibrium dynamics involving non-interacting many particle fermions. And then we turn on interactions, and we also keep the disorder on, and we find that for large delta and V, we get a big many-body localized phase. There is this sliver of a phase, which is the ergodic phase, when delta is tuned to some intermediate values when interaction is sufficiently high. But in the low delta region, in the presence of interactions, we get this sort of mixed phase with some delocalization tendency when V is tuned around delta. Right? All of these results are again sort of understood with the aid of a number of quantities. Some of them are static in nature, the others are dynamical in nature. Okay, that's all from my talk. Thank you. I can take questions now.
Thank you, Professor Sharma, for this wonderful talk. Let us thank our speaker.
Thank you.
So now we have time for a few more questions. If anyone. Nana, please unmute yourself. Nana, we cannot hear you. Nana, I guess your mic is off or set to very low volume because we cannot hear you. Okay, some technical issues. We cannot hear you, Nana. Okay, any further questions? Sergey, please.
Thanks, Auditya. Very, very nice talk.
Sure.
I have one question about your view on this difference between well, I'm not sure how you call it, the Anderson localization and this. So this is actually coming from the single particle part.
Right. Right.
So you stress this difference between Anderson localization and well, flatband localization, I think you called it.
Right.
But
right.
in some sense, it's the same as Anderson localization, isn't it? So,
yeah, it's just that it's a bit weaker than Anderson localization.
But the Anderson localization, I mean, there's a control parameter. I can always make a state more or less localized within Anderson localization, so to say.
Yeah, so that's true. It's just that we seem to have a fairly good understanding of the nature of the eigenstates involved in this kind of localization. They're all connected to this compact localized eigenstates, and they're all getting connected with some coefficients and forming these eigenstates, which are still localized, but they're able to spread out in the lattice a little more than the usual kind of Anderson localization. But other than that, yeah, if you look at just the energy spectrum, then they're all the same. It's just 0.386. So, I mean, yeah, one could argue that it's really localization, but it's just a matter of degree. It's a weaker kind of localization, but I mean, the reason why we give it a different name is because there is this underlying different principle which is playing a role, right? Which is
so at this, let me ask the following question. So at this crossover point, somewhere there is this crossing over from, say, this flatband localization, as you call it, to Anderson localization.
Right.
And this happens at a characteristic value of delta.
Yeah.
What happens to the spectrum of the single particle problem there?
Yeah. So.
Yeah. So somewhere there.
So what is this delta critical? Yeah. I don't know actually. Yeah. I mean.
It is not really a sharp transition, is it?
It's like a crossover, perhaps. Yes.
Yeah, but what I'm asking is what happens with the spectrum of the full system around this crossover region?
I guess it's not very clear from the spectrum. It just looks the same, I guess. For any value of delta, the spectrum has this broad structure which is the same. But it's only in the eigenstates that we're able to make out this difference when we look at the eigenstates.
And another question is, can you show please again this phase diagram, which
yes.
I couldn't find it in your paper. So you didn't, is it in the paper also, or did I?
Well, I mean, we tried to send it to PRL and it was there in that one. And then I got a different version, and that the version which finally got published doesn't have it.
Okay, so I couldn't, so thanks. Right, so if I go with delta down to small values, essentially approaching the CL, so to say, value, so 0,
yeah,
and I increase V, I will always be ergodic, isn't it, right?
You're talking about this region, this very close to the
yes.
CL?
So I want to make delta very small, but V very large. So I'm very close to the x-axis and marching to the right, the right-hand side. And then it seems
I don't. No, not ergodic. I don't think it's ergodic, but it's going to be actually localized. No, it's like I think you will go into a Mott insulator type phase. If you just if you make delta equal to 0 and V very, very large, then you get localization, I would think. But it's not many body localization.
Thank you. And what means mixed here again? I probably missed.
Yeah, so mixed simply means that it's neither really like a localized phase nor is it ergodic. So for example, if you look at R, it's neither 0.386 nor 0.529, but somewhere in between. And all other quantities also have this type of behavior. MIPR, for example, it's neither just 1 nor is it 1 over D.
So what is it then?
Yeah, so it's some of these eigenstates are localized. If you look at every individual eigenstate, some of them are more delocalized in nature, others are more localized. So you cannot make a broad statement about all the eigenstates. That's what is meant by mixed. Whereas in an MBL phase, I think all eigenstates basically contribute to are localized in nature.
Well, you could have a mobility edge, right? And you could have some states being localized and some being metallic.
Yeah, that's right. Yeah, so I mean, that's what happens here, right? So when we look at, let's look at this energy resolved picture. Yeah, so you see that some of these eigenstates seem to have these peaks, which is a tendency to go in the direction of localization. And then there are other states which are more delocalized in nature. So if you take some average value like R does, R takes all these eigenstates and just tries to find one number associated with it. So you get neither of this kind nor of the other kind.
Okay. Yeah, and to maybe add to your already the reference you gave to this paper of ours on the purely ordered system with interaction with, so you can find basically specifically chosen interaction types, which together with the so you have the single particle problem, say, which is all bands flat. Then you add fine-tuned interaction.
Right.
Then it turns out that you will stay localized, meaning you will have complete localization, no transport.
So that's a kind of many body like localization. Are you able to work out these integrals of motion and stuff, right?
Yes. Except this is the exact and provable and okay, and maybe in some sense also more trivial. You could say, if you add disorder, probably it will always be destroyed. So the question is whether your model, whether your type of interaction which you consider here will lead also to this many-body flatband localization, as we called it, in the absence of disorder.
I see. Yeah, but I mean, we are getting this mixed phase here, so I don't know whether it's we don't really have
but this is for non-zero disorder. So
right. Actually, yeah, I think we did not study this the x-axis carefully enough. Yeah, perhaps it's worth looking at it more carefully. Yeah. Okay, and maybe there is an MBL phase sitting there, a different kind of localized phase.
Thank you.
Yeah.
We have another question from Meng. Meng, please unmute yourself.
Hi everyone, I'm Nana. Sorry, I had some sound problem in my desktop. So what I'm going to ask is that, so the way you get all-band flat system in diamond chain is that you just change one sign of the hopping term in the Hamiltonian, right?
Can you say that again? I don't.
I mean, what I'm asking is, could you please go to just the beginning?
Right. Okay.
Yeah. So the way you get all-band flat system in the all-band flat, just change the second term in the hopping, right?
That's right.
Minus,
so if you look, yes,
so
exactly.
I'm just wondering about this CLS structures. Could you please just give some comments? Because what I'm knowing is that just CLS is in diamond chain is +1, 0, and -1 unit cell. So how can we I mean, could you give some comments about the CLS structures?
Yeah. So the thing is that if you take this model as it is, this hopping model, and you don't put this minus sign, then you will get just this one flat band in the center, but the blue band and the red band are not going to be flat. They are going to be dispersive bands. But if you put this, if you take one of these bonds alone to have a negative sign, then it so happens that all of these bands become flat.
I see. So you just check this spectrum, or if all bands flat, then it's CLS, right? This is the way you check this.
Yes.
I see.
So I think, I mean, all credit should go to Ajit, because he was the one who told us about this. I didn't know about this system until I started talking to Ajit. And so he told us that, Yeah,
this is very interesting. So I have another.
Indeed.
So could you just also about this problem? So why, if we change this just minus, we just change the sign and this system can become all-band flat system? So is there something special for this?
Yeah. So there is this game you play with. You start from a site and then go to the neighboring site, and then it has to close around, and you have to sort of engineer it in such a way that it supports a compact state, right? So I guess it's just a game you play. There's a lot of sort of trial and error involved in it, and then if it works, it works. But once you have it, then you can say that, oh, okay, this is a flat band supporting system. But I guess there are also well-defined ways of engineering systems which can give you flat bands. I think Alexei has a paper on this, although I have to confess that I don't understand it completely.
I see. Thank you very much.
Yes.
Okay. Do we have any further questions?
Yeah, I have asked for a question. Can I ask?
Yes.
Yes, sure.
Sure. So the question is the size of the system, N capital. Is it important? And it actually separates in two separate questions. The one you have discussed already during the talk, what happens when delta goes to 0 and you have to go singularly to the value 1? I would expect that delta maybe should scale with N, and you can obtain only thermodynamic limit that you jump up. And the second question, do you have any typical size of your compact localization and your Anderson localization? If you have system N equal to 18, what is the size of localization?
Okay, so I did not quite hear the first question, but let me try and answer the second question first. So yeah, compact localized states are just over 2 unit cells, right? So it's just 1, 2, 3, 4 sites, right? It's well defined there. But Anderson localization tends to go over many sites. So there is a localization length associated with it, but it's exponential localization, but with a tail. But we did not really compute this localization length or anything. But it's but I mean, as you see from this figure, for example, let's see, look at the dynamic result. So this black region is it's like a length scale for compact localization, but the region inside which your green curve is spread over, that's like a length scale for your Anderson localization, right? But I mean, I don't have a correlation length, Anderson localization length here.
What I meant is, I mean, if your results are not affected by the finite values of M capital. And second one, what I meant is if you look at your phase diagram you have started with,
right,
on the vertical axis, and
yes,
you exactly go to the yes, here from the red button up.
Yes.
You expect that for delta equal to 0, you can see something which is completely different from the small delta. And
that's right.
This transition can be seen, and it should be dependent on the size of your numerical system. Okay, thank you.
So all the quantities that we studied, we cannot just tune delta from 0 upwards. We always set delta to be like 10 to the minus 3 or some small value, right? Even for IPR, for Fidelity.
To previous time, exactly. What would happen if you would like really to go to 0? I mean, how it is?
Yeah. So the problem is then you have you have to work with these compact localized states and this massive degeneracy. So which state are you really considering? That becomes an issue there, right? I mean, you can take any two degenerate states and form an arbitrary linear combination of them, and then if you compute IPR, it's going to be a different number altogether. So it's not really clear what quantity you're studying if you're sitting at the point delta equal to 0.
Okay, thank you.
Okay, do we have any further questions? In case not, let us thank our speaker for this very nice talk again.
Thank you. Thanks a lot for the invitation. It's a pleasure.
Okay, and thank you all for joining. And with this, we conclude the official part